Hello everyone, welcome to my YouTube channel of subject Basic Electrical Engineering, and in this subject you are studying a concept of AC circuit. In previous videos you have seen analysis of different type of AC circuits. We have started from pure resistive circuit, pure inductive circuit, pure capacitive circuit, series RL circuit, series RC circuit, series RLC circuit. And in case of series RLC circuit, we have seen one concept in two cases, and that concept was the phasor diagram. And that two cases was what if VL is greater than VC and what if VC is greater than VL. But one must have a question, what if VL and VC is having the same value and they are 180 degree apart from each other? So obviously they cancel out each other. And in that circuit only resistive effect will be present, and that condition at which VC and VL becomes equal, it is known as the resonance in series RLC circuit. So today's video is all about the resonance condition in any series RLC circuit. So to understand the concept of resonance, we must need to recall the same circuit as we have taken in series RLC circuit. So this circuit is having three elements connected in series, that is a resistor, inductor and capacitor. V is the applied voltage to that circuit and I is the current flowing through that circuit due to the applied voltage. VR, VL, VC are the voltage drops across resistor, inductor and capacitor respectively. So if we draw the phasor diagram of this series circuit, then the phasor diagram will be, first we have to take current as a reference, because in series circuit current flowing through each element is same. So we have to take current as a reference. On the current line there will be the voltage across resistor, because in case of resistor there is no phase difference. In case of inductor, current lags behind the voltage by 90 degree, so voltage leads from the current by 90 degree. So VL will be on the above of this phasor diagram, upper side of this phasor diagram. In case of capacitor, current leads the voltage and voltage lags behind the current by 90 degree. So the VC, that is the voltage across capacitor, will be on the downside of this phasor diagram. So we have seen this phasor diagram earlier also. But here we are talking about the case where VL and VC is having the equal value. So if VL and VC is having the equal value, then this condition in any type of series RLC circuit is known as the resonance condition. So if VL and VC are equal, then we can say that VL minus VC or VC minus VL becomes 0. So there is no voltage due to inductor and capacitor. So if we are putting the values of VL and VC in that equation, then it will be IXL is equals to IXC. So if II is cancelled out, then we can say that XL is equals to XC, or we can say that XL minus XC is equals to 0 or XC minus XL is equals to 0. So in case of impedance also, there is no effect of inductor and capacitor at this moment where VL is equals to VC. So the impedance Z was under root R square plus XL minus XC square, but that XL minus XC square will be eliminated, so it will be Z is equals to R. So impedance will be minimum at this condition, and this condition is known as the resonance in any type of series circuit. And if we talk about the supply voltage, so earlier supply voltage was distributed into three components, that is VR, VL and VC. But now we have the equation of voltage as V is equals to under root VR square plus VL minus VC square, or you can say VC minus VL square. But in this case, VL and VC is having the equal value. So VL is equals to VC. If we put in this equation, then that part becomes 0. So the supply voltage will appear only across the resistor. So this condition is known as the resonance condition in any series RLC circuit. So now let's talk about one resonance frequency. So that means it is not obvious that always inductor and capacitor is having the same value. or you can say the voltage across inductor and voltage across the capacitor will be having the same value. If you want to make the same value, then what you have to do is you have to make XL is equals to XC. And if we make XL is equals to XC, then and then resonance condition will be appeared in this series RLC circuit. So when XL is equals to XC, so there is some frequency, because XL is equals to 2 pi FL and XC is equals to 1 upon 2 pi FC. So basically XL and XC both are the function of frequency. Means as frequency changes, XL and XC will be changed. So that means at some point of frequency, at some values of frequency, this XL and XC will achieve the same value. So let's find the equation of that frequency at which XL becomes XC, or you can say that XL is equals to XC, and that frequency is known as the resonance frequency. So to define the resonance frequency, we have to take first equation as XL is equals to XC. Put the value of XL as 2 pi FL and put the value of XC as 1 upon 2 pi FC. So if we are bringing frequency on one side and all other terms on other side, then it will be F square is equals to 1 upon 2 pi square into L into C. So if we are taking under root of this F square, then it will be F is equals to 1 upon 2 pi under root 1 upon LC. So this equation is known as the equation of resonance frequency. So in this way you can find the frequency if you know the value of inductor and capacitor connected in that series RLC circuit. So you can find the value of frequency at which resonance condition will appear. So this was all about the resonance frequency. So now let's understand the next definition, and the next definition is Q factor. So Q factor is nothing but the voltage magnification, because at time of resonance the voltage across inductor and voltage across capacitor will becomes extremely high value than the supply voltage. Generally it should be not that. That means supply voltage will be always having the higher value and the voltage drop across element should be having the less value than the supplied voltage. But in this case of resonance, our voltage magnifies. So this Q factor is nothing but the voltage magnification value. That how much our voltage across inductor or voltage across capacitor is greater than the supply voltage. So basically Q factor is the ratio between voltage across inductor or voltage across capacitor to the supply voltage. So let's find the equation of Q factor. So Q factor is equals to VL upon Vs, where VL is the voltage across inductor and Vs is the supply voltage. So let's put the value of VL and Vs in this equation. So VL is nothing but the voltage across inductor. So it will be I into XL, and the supply voltage at resonance condition is having the value IZ. But we know that impedance Z at resonance is equals to R. So instead of IZ, we will use IR. So if II will be cancelled out, then the Q factor is given by this formula. Q factor is equals to XL by R. So now let's put the value of XL as omega L. And we know that omega is nothing but 2 pi FL. So now the Q factor is having the value as 2 pi FL upon R. So this 2 pi FL upon R, in this equation 2 pi L and R is constant, but F is nothing but the resonance frequency. You can put the equation of resonance from the last previously derived equation. Fr is equals to 1 upon 2 pi under root 1 upon LC. So if you put that equation in this equation of Q factor, then you get the answer of Q factor as 1 upon R under root L by C. So this is the equation of Q factor. From this equation you can find the value of the voltage magnification, means at time of resonance how much voltage across inductor or capacitor is increased than the supply voltage. So this was all about the Q factor. Now let's draw the graph. And this graph is known as the graphical representation of resonance condition in series RLC circuit. So we know that this resonance condition will occur in any type of series RLC circuit at some frequency, and that frequency is known as the resonance frequency. Means all the parameters are correlated with the frequency. So we need to draw the graph with respect to frequency. So let's take one x-axis and y-axis. So we have taken one x-axis and we have taken one y-axis. On x-axis we have taken frequency because we want to draw the graph of this resonance at frequency with respect to frequency. We want to define all the parameters with respect to frequency. And on the y-axis we will take so many parameters. So let's first take resistance. Let's draw the graph of resistance with respect to frequency. But we know that resistance is independent of frequency. So at x-axis and y-axis from origin, resistance is having some value. And that value is fixed till our experiment continues. So we can say that resistance is a straight line with some magnitude. Now let's draw the another graph of inductive reactance XL. So we know that XL is equals to omega L, or you can say that XL is equals to 2 pi Fi. So basically we can say that XL, that is the inductive reactance, is directly proportional to the frequency. So if frequency is 0, XL will be 0. If frequency increases, XL will also increase. So it will be a straight line passing through origin. So this is the graph of XL. Now let's draw the graph of XC, that is capacitive reactance. But we know that the formula for capacitive reactance XC is equals to 1 upon omega C, or you can say that 1 upon 2 pi Fc. So from this equation we can say that XC, that is capacitive reactance, is inversely proportional to frequency. So that means if our frequency is 0, then XC will be having the highest value, or you can say it is infinite. And if frequency is infinite, then we can say that Xc will be 0. So the graph of Xc will be drawn like this. At 0 frequency, Xc is maximum and Xc will be decreased as frequency will increase, and at some point Xc will become 0. So this is the graph of resistance R, XL and Xc. Now we need to draw the graph of impedance Z. So if you want to draw the graph of impedance Z, then you must know this XL and XC is meeting at some point, and you have to locate that point on the resistance line as well as the frequency line. Because when this XL and XC line touch each other, that means they are having the same value. XC was maximum but XC was decreasing, XL was minimum but XL was decreasing. For example, if XC is having the value 100 and 100 is decreasing, and XL is having the 0 value but the 0 value is increasing. So at some moment XC will be decreased about 50 and XL will increase about 50. So at this point XL and XC is having the same value, and this point is nothing but our resonance point. So the graph of Z will be having the value Z is equals to R at that point. So you can see the graph of impedance in this, and this graph of impedance is having the higher value at initially because XC is having the infinite value and XL is having the 0 value. So it will start from infinite and it will start decreasing because XC is decreasing from its infinite value. At some point where XL and XC is equal, then the impedance is having the minimum value as resistance R. So it is touched over the resistance line. And again XL is going towards the infinite and XC is going towards the 0 value, but XL is going towards infinite. So again the graph of Z will be increased. So this is the graph of impedance Z. After impedance graph, we must need to draw the graph of current, and we know the equation of current as I is equals to V upon Z. So that means if impedance is maximum, then current will be minimum. If impedance is minimum, then current will be maximum. So you can see this is the graph of current. So if graph of impedance is drawn like this, then graph of current will be drawn like this, just opposite, just mirror image of the graph of impedance. So this was the graphical representation of resonance in series RLC circuit. If you are talking about the power factor, then you have seen that before this resonance frequency, the effect of capacitive part will be high. So you can say that power factor is in leading before resonance frequency. After resonance frequency, inductive effect is more, so the power factor will be lagging. But exactly at resonance point, there is no effect of inductor or capacitor, only resistive effect is there. So at exactly resonance point, the power factor is unity, or you can say 1. So you can draw the graph of power factor. Just similarly, you have drawn the graph of current. So that means power factor is in leading, power factor is unity, and power factor is lagging. So this was all about the resonance condition in series RLC circuit. Thanks for watching this video. Stay tuned.